Okay. So it took me a while to get into your homework. I should have done it right away. What do you guys think about it? Reread. What? Yeah. Are you passing the class? Are you doing effort to pass the class? I don't know. Okay, I can see it. Okay. I haven't gotten any of the homework ones back. I haven't had anyone come to office hours except for Dante. Okay. Homework 3, due on Thursday. Okay. You need to be putting in as much effort per week as you would for weekly homeworks. I can change it so you get them every week, but I don't know if that will change it. Right? Are you reading the book? Are you looking at lecture slides? I'm trying my best to understand how every single one of you can get 4 solo without asking me a question. Scary? So the question says, consider a planet of radius with density that decreases linearly from center to edge. We did it in class, right? So it's on record, and there's lectures. And if I go to here, the week 2 thermodynamic, where is it? Come on now. Oh God. Right? Temperature in the interior of a rocky planet. Right? Right there. So I kept some notes. They're pretty minimal. 4 and 5 have no notes. I'm happy to work through them with you. If you want to talk about the math. But this is not a lower division class. This is an upper division class. I would love to give you all A's, but I can also give you all F's. And that's not something I want you to do. Right? Like, there's no reason that you need to retake this class. Okay. If you're stressed about other classes or stuff is piling up, that's okay. Do an extension. But turning in a homework that's not complete and you have 2 weeks to do it is unacceptable. Especially when you don't come to talk to me about it. And if you're struggling on something, great. Right? When you were doing the creator campaign, I got a lot of really good questions. Not a question about 4. Not a question about 5. Okay. It's only going to get harder. Dynamics is not simple. It's hard. So if you're putting in low effort now, you're going to be at the very end of the class. You're going to hate it. Okay. But if you care about planetary science, you have to know this. And in particular, these types of equations, right? We can break this down. We can talk about how this works. But understanding this sort of spherical geometry, right? Why do I have a dr squared 1 over r squared on this side? That's just from the fact that it's spherical. Right? So I saw a couple people I was impressed with. They started here. Right? I'm like, oh, that's great. You know, at least you thought about the fact that it's a differential equation. But you didn't take into account that it's circular, not radial. So if you forget to do that, you're going to be off by a lot. And I saw some really good explanations for the work that they did do. Right? So people who really investigated their own work, there's just such a simple error at the beginning that the rest of it is useless. Okay. That's my bad. I should probably have looked at them immediately and said, hey, everything's broken here. But hopefully, that doesn't happen again. Which one of these are we doing today? Oh, yeah, okay. So how familiar are you with orbital dynamics? You taking classical? Currently taking classes. Currently taking classes? Okay. So you've seen like energy potentials before. And in 2500, you saw like kinetic energy and stuff like that. Okay. So we're gonna have to skip over a couple slides and we'll bring them back up. We're gonna start talking about like how orbits and everything work. We'll finish up the discussion of rings and perturbations. And in particular, we'll talk about the tidal radius. And then we'll just go from that into orbital mechanics. You'll be learning orbital mechanics for the first time. So if it's daunting, the math doesn't make sense, I really need you to step up and be like, look, I don't get it. Right? Not just in class. But if I see you go, oh, okay, in class, and then you're not getting it, it's gonna be 2 weeks before I see that you're slammed, right? You don't want to be underwater with this material. It's counterintuitive, it's math heavy. There's a reason why people have been doing it for 400 years. Okay. Okay. So we were talking about the hill radius. What was that? U2 times. Good, right? So you have differential pulling, right? The closer thing is getting pulled more than the interior, and that's going to break apart the internal gravity, right? We'll talk about that. We're going to talk about resonances and perturbations. So over the course of many millions of years, the idea of resonances becomes much more important and how do we treat them. We'll talk about all of the structure except for horseshoe and tadpoles, because this requires a little more clinics than we have today. We'll talk about shepherding, and then we'll talk about the moment of inertia. So here you have the ring structure, and you have to scale different objects. So you have a moon minus, I believe, and Titan, and some moonlet. I forget which one. Oh. Yes. There we go. Okay. So this is what we were talking about, right? You have some effective gravitational acceleration. So what does this mean? This effective gravitational acceleration. Why is it not just the gravitational acceleration? Okay, good. Yeah, so let's say I'm at this location right here. And I remove this body. I'm just sitting right there. What about this configuration? Gives me 2 terms. This one I know, right? What's this one? Yeah, gravity from the big body. What's this one? Is it? A is the distance, right? Okay. What's this one? Rotational acceleration. So I have an acceleration that pulls me inward, that's gravity, balanced by the fact that the frame that we're in is rotating. And therefore I'm flown off. So think about it like this. You have a CD or a carousel, and you're standing on the carousel and then you spin it. What happens? Yeah, accelerate. Have you ever been flung backwards? Have you ever had a ball fly off? Put a ball on the carousel and you spin the carousel and the ball goes flying. That's this, right? You're being flung out. It's not being balanced by the fact that you're being pulled. So your acceleration at this location is less an issue. Okay. Good. We found out in the radial direction, you could write it like this. So we take this differential acceleration we do the differentiation, and then we add these pieces together to get how much. This leads us to the definition of the hill radius. Okay, and that just says that when the gravitational acceleration of the body inward on itself is equal to the pulling from the body nearby, I can rearrange for that delta H, or sorry, that delta R, as that distance away. And it looks like that. This one, remember, is different than the one you just saw. You saw the Roche radius, and that was in terms of densities. Okay, so here I'm making an assumption that they're the equal density, and I want to think of them in terms of mass. That's still legal? Okay. So what is their equal mass? If I'm asking, let me ask you a more specific question. What is the hill radius when they're equal mass? Is that what I'm asking when I talk about the hill radius? It's a balance of forces, right? So on one side here, here I have object little m, okay? And it is a circle with stuff that is pulling it all in towards the center, right? Okay. And this force here is its internal gravity. Right? And then I have another body over here, also in space somewhere, maybe with big M. And it's also pulling from this point here. That wouldn't be a problem if it was just a dot. But the fact that it's large means that there is difference in pulling all along points. Every point here, it pulls less. So like it's here, that's pulling the maximum. This is pulling the minimum, right? So there's a balance in forces. This is the force from the other body. I'm asking, when are they equal? Because when they're equal, this piece here will feel just as attracted to the center as it will to its neighbor. Okay? If this one's larger, what happens? Right? And there's no room for it to be there anymore. It'll start moving. It'll lift off the surface of the moon. The moon will become disrupted. Right? This is the definition of the Roche radius for the hill, depending on whether or not you're talking about density or mass. Okay. So when I talk about RH here, and I write the radius is equal to A divided by this. What am I saying? The hill radius. It's like, what does it mean? Okay. Yeah, so this rate is the distance between them, right? This is the mass of the little body, this is the mass of the big body, and this thing here, as Zori is pointing out, is the radius at which you're so close to the bigger body that it feels more force towards the bigger body than it does to its itself. Okay? Only happens in two bodies, right? Never have a hill radius without considering a nearby other body. This is the distance between them and the ratio of the mass. If they're equal mass, m,
Then it, I guess they would both feel the same.
yeah, we'll feel the same amount, right? Okay, think about how this works now. We flip this over, let's say this is the bigger one, and this is the smaller one. Yeah, what happens here? So let's say this is 10 and this is 1. Well, think about what these actual numbers are. Like, take this to be 1. Say 180. Okay, let's say one object is 10 times larger than the other. What's in here? Okay, 10 is approximately 9. And 9 cubed is, well, that's 9 squared is 3, but less than 3, right? 1.5. Okay, so the hill radius for an object that's larger than its friend is larger than the separation between them. Right? It's not worried. Big one's not worried. Flip it around now. Okay, but let's see, 1 up here. Let's put 9 down here. Okay, 9 times larger than its friend.
Yeah, like what you're saying, 1 over 1.5 approximately.
Yeah, so 1 over 27, for example, is a third. Right, so if the body on the bottom is bigger than the body on the top by a factor 9, then the hill sphere becomes a third of an AU. So now these two things can't orbit each other within a third of an AU, otherwise the smaller one begins to disintegrate. Does the bigger one start to disintegrate? Not weird. Right? So this here describes the sizes that we should expect to find in the gaps in the ring. Because if, for example, you have a shepherding moon, what will it do to nearby particles? Suck them up, I don't really like to say because there's no vacuum in space, there's no like suction, but it's gravitation, right? It's attracting them, right? So it's gonna swallow them. Yeah, same way of thinking about it. They're gonna fall. They're gonna start over here in their little clump, and they're too close, and they're gonna fall into the parent body. Right? Even though they're both going around and rotating reference frames at the same rate. That's the claim. That's the claim. We'll see if we see it. Okay, so here's a spherical body with a diameter of 7 kilometers and a density of ice 1. It's far from Saturn, has a hill sphere of almost 7 kilometers. So here it is, 7 kilometers. Look how big the gap is. Now, if I take my finger, almost the same gap size there, a little bit less, maybe that same. Okay. So this body is grabbing these nearby ones and pulling them towards it. Now we understand why there's waves. This one here is getting pulled as it passed by, right? So it's moving this way faster than this. It's creating waves behind it. This one moving slower, it's getting pulled direction. Right? Okay, so we can, yeah.
The hill rate is, was like is from the body to the ring, right?
Yeah, so it's the distance between them like this. So you have to think backwards, right? So this is now the Keeler moon. It's from the dust particle to the object, right? So the dust particle itself is getting pulled. Good. All right. We haven't learned this yet. You will learn this, and we'll talk about it in a lot of detail when we talk about how orbit transfers work. How do you move around in the solar system? How do you get to the outer solar system, for example? You know, you wrote the Clipper launch yesterday, so that would get to Jupiter in 2031 or 2030 or something. How's it gonna get there? Talk about that in this type of class. But the way you do that is by three forces. You know, in a perfect world where you have a star, perfectly spherical, not rotating, nothing else is happening. You have a planet going around like this. There's no other forces. Should do that forever, no? No reason for it not to. You imagine that there's no tidal forces, perfectly dot, and nothing changes. Okay, so the only way to change the orbit is to perturb it. Hence the word perturbation, right? To change it in some way. And this happens through forces or impulses. So impulses would be like fuel when you fire the rockets, or long-term forces, like something that's happening periodically and changing the orbit. Okay. When we say straightforward here, it's really important to know that these are not simple. They're just easy to say. So it will be very easy to conceptually understand this section of the class, and it will be very difficult to do. Okay, this is where mechanics and conception of mechanics differ, right? Because you're going to say, oh, I gave it a force here. And then, because the entire system has negative potential energy, you will not know what happens next. It's not a system that we're familiar with. Every system that you've seen on Earth, you roll a ball down the hill, right? It had positive potential energy, and it turned it into positive kinetic energy. Right? You never had a bound system held in your hand. Okay. So it's going to depend on where the impulses are applied, what direction they're applied, and how the orbital parameters can be changed in the context of this orbit. And the equations of motion, which we'll describe for how things move in space, can be used to find the points at which the impulses should be applied. Okay? So let's say, for example, you start in the plane of the orbit, going around an object like this. How do you go up? Out of No. Just imagine you have fuel. You're a rocket. Yeah, that would make sense, right? This. Go up. Okay. Let's say you're already going around in a circle. What if I want to go in? I want to change my orbit and make it smaller. It's weird. Very weird. Reducing speed will do something unexpected. Yeah, let's see it. It'll be easier to see. Hey. We're going to talk about all of these. It says in the past, these are old slides because I didn't know quite where to start today. Okay, here's how we can change certain things. Okay, here Okay. And that periapse, I'm closest to the planet that I'm orbiting. And I give it a big fuel boost. Okay, my original orbit is here in black. Okay, and I accelerate, right? I go faster, and not only will I now get out to a farther distance away from the body, sun, whatever you want to call it, I'll also increase my eccentricity. So increasing speed gets me farther out. Okay, that's great. That seems really normal. That seems really natural. But only right here. If I do it out here, and I increase my speed, I still get farther out. Increasing the speed increases the size of my absolute size of my orbit, but it decreases the eccentricity. It circularizes the eccentricity. Right? Okay. Similarly, if I don't do it in the direction of motion, if I do it slightly off to the right, and I'm heading in towards periapse, and I'm going off to the right, I'm going to increase my A. I'm going to slightly change my eccentricity, but I'm going to greatly speed up my orbit. Okay. Similarly here, it has the opposite effect. It increases the A, same as it did here. Small change in the eccentricity, but it slows down. Okay, this is really important to remember because we're going to think about it in terms of fuel going around in something like Saturn. Okay, going around Saturn, you're going around Saturn, you're going around Saturn. But now I want you to imagine none of the particles in the disk have fuel, but they do pull on each other. So we have this little moon, and I'm going to pass by that moon, and it's going to pull on me. And the direction of the pull and where I am in my orbit is going to change my orbit. Okay, so this is all then in the plane. Okay, now you need to bend your mind for a moment. Imagine this was the plane, now I've tilted it. Okay, does that make sense? Now we're going to have perturbations out of the plane. Okay. These are called normal accelerations. They're perpendicular. Okay. So let's apply them at the same places we did before. And I'm going to show you how it makes the orbit evolve. Let's start back here, the red one. We're going to apply it periapse. Okay. And now the orbit is going to tilt. That is something called inclination. How much is it tilted? Let's say here's our original orbit. That I applied a periapse. Cool. That's fine. It's not bad. That one makes sense, right? Okay. Let's say I'm over here. I do it on this side. What does it do? You'd think it would go up like that, right? Increase inclination. It decreases the inclination. Just like in the previous example, when I am at apoapse, when I'm at the farthest away, when I'm at the farthest away, and I give it a little push, I increase A again, but I decrease E. I decrease the eccentricity. So when I'm farthest away from the body, and I perturb it, I decrease I, decrease E. And similarly, when you apply them to those two places, just on either side here, you're going to tilt it. Okay. So now what you're going to do is you're going to move the orientation of the, so let's say this is the ellipse. Now I start it rotating like this. The body that I'm orbiting is in the center here. I'm orbiting around it. That's called precession. And we saw that precession with Mercury, right? Precession. Okay, so the direction of the orbital precession applied before you get the closest part makes you go clockwise. So now the tail is going to swing to the right. Applied after you go through the closest part, it's going to swing the opposite direction. Is that intuitive? No, shouldn't be intuitive. Okay, let's do another one. Radial acceleration. So now I'm going in the direction of motion and I fire opposite to my motion. Okay? No change in A or B. So at this point here, and this might be important, right? Let's say I'm getting close to Saturn and I get pulled out. The only thing that happens is that I speed up along my orbit. Okay, my orbit doesn't change. Similarly, when I get out to the very farthest point and I get pulled, then I slow down. Doesn't change the orbit though. And if I get out a little far away, now these are the examples, right? This almost never happens. Usually you're getting pulled any other part of the orbit. So this one here is very interesting, right? So now I travel along, I get pulled, and I'm getting pulled out radially. Look what happens here. I'm getting pulled out. A and E increase. That's exactly how we thought of it before, right? The only difference was I was getting pulled in the line of motion here. So now I'm getting pulled here, A and E increase. And if I continue to get pulled along my orbit, it's still going to get larger. A and E are both in it. But if I'm headed home, I'm going back home, and the radial acceleration is outwards, say behind me. Okay, so it's always going to be radial, so it's going to be pointing out this direction, all the way until I get into here when it's pointing that way. Okay, so if it's pulling up that way, then I shrink it. So if there's a massive object in front of me, okay, and I'm on this part, there's a massive object in front of me. What happens to my orbit? Getting it pulled towards the massive object. Let's imagine that I'm out here, massive object. My A and E are going to increase. Am I going to go directly to the massive object? No. In fact, it's probably, it's probably going around its busy life and it's moving slower than me, so I'm probably going to pass it. But I've now altered my orbit such that it's a bigger orbit with more eccentricity. Okay, so first it pulls me out, makes my orbit bigger. Now let's say I'm passing a different object, and it's more massive and it's out here. Now what happens? Decrease, right? So now I'm shrinking again. So this is all very okay as long as I get the same number of passes. It can be a stable system, right? Shrink and grow, shrink and grow. Yeah.
So when you're shrinking and growing, your orbit speed is still the same though?
Yeah, in those circumstances, yeah. Okay. Okay. So, if you're just getting them randomly, it's fine, evens out. But if I'm always, let's say, okay, let's say I always meet my cousin or this big piece of mass right here. So we are in an orbital resonance, such that every time I go around twice, he goes around once, he's always right here. Now what happens? Now I don't get the nice canceling effect of seeing him over here. And I keep adding. Yeah, my orbit's going to keep getting bigger and bigger, and the eccentricity is going to get bigger and bigger. So those tiny little perturbations, they start to matter. Because it was just a small amount of A and E, right? We've exaggerated it here for their sake. But it's small until you have the resonance. Now, if you see the same object millions of times, then you can get a substantial amount of growth in whatever the object is you're trying to get, right? Okay. So for example, we can get normal perturbations that drive vertical oscillations. This, right? We imagine we have this, and I'm going to perturb it in this direction. It pulls up, it pulls on its nearest neighbor, creates a wave. Up and down. And it's gonna have some harmonic motion. It's just gonna go up and down. Up and down. They can also drive radial oscillations. So for example, here's our disk. I can get waves that go this way. And going around like that. I can get waves that are going out. So here's the different ways we can think about this. The location has angular frequency, big omega. Then there are some natural frequencies associated with it. So the vertical oscillations, the one that go up and down, are nu. That's like a V-looking one. Radial oscillations are kappa, one going back and forth in the disk. And the angular frequency, the one that's going all the way around like this, is the big omega p. Okay. That makes sense. So this is the orbital angular of the object. This is the perturber. This is the angular frequency, that location. This is the radial acceleration. And we can just add those. You can have any numbers in there. H, I, J, K. Okay. And if this thing, right, the perturbations become resonant if that's approximately equal to 0. You'll see why that is in a few seconds. This is called the Lindblad resonance. You don't have to memorize that. You will see it if you go to that. So you'll notice that there is a little bit of, it's not just the perturbation of some object with the orbit. It's also, is there a natural up and down that's mixed in, right? That's the H here. And is there any back and forth wiggle in the direction it is here? These terms make sense? Okay. Up, down, side to side. Your orbit, the thing perturbed. So if you're in a 1 to 2 resonance, 1 to 2. If you're in a 2 to 1 resonance, 2 to 1. That sort of make sense? Okay. Okay. And then we see these waves all over the place. So let's start on the left-hand side. We have all of these particles, and they're just going around in perfect little circles, and everyone's happy. But they are being pulled by everyone else. So let's say that you're here, right? You're all accelerating around something in the middle, but I'm not that worried about that. Think about that for a moment. So we can use that G effective that we had, the fact that it's rotating, and you can just imagine all of these particles are rotating with all the same speed. Right? Okay. The rotating speed. So now this one here sees the nearby, the forces to these two on either side, those are balanced, right? So it doesn't care about the stuff in its own ring, but it does see the stuff in the nearest ring. And it's getting pulled out. Now in a circle, you get pulled out, what happens? You get bigger and you get eccentric, right? So you start with a circular orbit, you pull. Right, there's no periapse, there's no apoapse in a circular orbit. So you pull on it, and it gets bigger. So now it's closer to this part. Right? And if it's closer to this part, then it's going to see more of it. And so you start to have bunching. Right? But as this ring moves apart from its friends, now you have an unbalanced force on the two nearest neighbors, because on one side you have material, and the other side you don't. Right? So now that change, as this compresses, it pulls on all these guys, from the left and right, pulls them out of their orbit, and it twists, makes an impression here, and this is twisting all the way out. These are the spiral density waves that exist here and also in the spiral arms of the Milky Way. This is exactly the same phenomenon. This is material grabbing nearby material and forcing it to be close to one another. It's a trick. Right? And so you get these beautiful little spirals. That wrap around. Okay. Now, of course, when you get to do galactic dynamics, scales are very different. You know, that's happening over maybe 200 million years. And you don't have pesky stuff like changing the orbits of the individual particles based on how much light they receive. So light carries momentum, and we'll see later in this class that just absorbing light will change your orbit. Stars. Okay. So those are spiral density waves, and this is how it looks when a satellite goes by. Right? So this one is moving faster than this one in a relative sense. And so the perturbation is strongest here, and it's dying off as it moves farther away. Okay. Okay. The amplitude of this bending, the vertical bending, can be 1,000 times the thickness. These particles can come way out of this. So those are the bending waves. We're going to skip past, oh, wait, not this one. This one's cool. This is just an example. So these are waves at the 5-3 resonance of lithium-ions. And inner wave here on the right is a spiral bending wave. So you can see each of these wave patterns. If you go back here, something. So this is vertical, up, down. Right? This is a vertical, up, down wave. These are spiral bending waves like this, going backwards. So you can see in this structure how these waves propagate into this. Okay. So it has vertical position oscillations. It has these radial oscillations as well. And the reason you can see it, okay, the reason you can see these waves here is because these are, this is like the top of the wavelength, and then this is the shadow. And then this is the top of the wave, the next wave. And this is the shadow. Does that make sense? What you're looking at now? This is not density. This is up and down. Right? So just like you look at crater walls, and on one side it's light, and on one side it's dark. That's what you see. So these are just fluctuation. That's one here. That's another one. This one on the left is the spiral density wave, and that's the radial acceleration. That's what it's compressing. Right? Here's more of them. Same set of waves, or a similar set of waves in the A ring. Great. It's easier to see on that side? Yeah.
Well, yeah, just at the angle, and it's compared to the last one.
Yeah. Pretty well, right? Okay. This is orbital dynamics at its finest, right? So this is like your ability to predict the amplitude of these waves. We're going to skip this one when we talk about horseshoe and tadpole orbits, but remind me to come back to this after we've talked about Lagrange points. So that would be the place where in a two-body system, I'll just talk about it really briefly, but we'll do the math on it later. In a two-body system, let's say they are sufficiently far enough away that they're not pulling each other apart. Okay, so you have big M, you have little m. Okay? That doesn't look like a little m, but it's supposed to. There we go. Better? First place. Okay, so there are a bunch of places here. Okay, between these, this is some distance, big R. Think of that as like 1 EU or whatever. There are 5 places where a particle feels equally pulled towards M and little m. Where are they? Very important question. Well, if they were not moving, what would happen? They crash. Yeah. So this is a very important question. Let's say that the entire frame is rotating with the speed of omega. Okay, so in fact, there's 3 things that have to be considered. 3 balanced forces. So the net force is going to be equal to what? So vector. We're not going to do the math here. I'm just just the word. Yeah. So big M on the one, what does that mean?
Mass of the big object.
Right. So the gravitational acceleration of big M on the object of interest. Some particle. Okay, what else? What? Well, plus the force of the little guy on some object. What? Yeah, the force of the rotation. So the rotating. Okay. Good. That's conceptually it. Right? You're like, oh, sick. That seems super easy. Super fucking hard. So we'll do this in a lot of detail, but I just want to show you the results first because it's so beautiful. So the first one makes a lot of sense actually, and you're going to get it right away. Where is the first place that the forces all balance? So that you have no net force. The Lagrange places, Lagrange points on where F net equals 0. There'd be a long arm where. Yeah, so let's say M is bigger than little m. This way or this way? This way, right? Everyone okay with that? You guess that intuitively? Okay, here's one. That's the freedom. So if I go out of the plane, there's some location here for those forces, right? Okay, so there's one up there. One below it, right? Gotta have some symmetry. We love symmetry in physics. Good. We got 3. That's pretty good. You're only missing 2. That's 4. This is where you get the evil Earth hypothesis. Yeah, so because in a two-body system, you can hide a body on the other side with the sun in the way. You can't see on the other side of the sun, can't see through the sun. There is a very funny, untestable science hypothesis because if there were a body on the other side, our evil Earth, we have no way of knowing. Now, of course, it's not exactly correct because you would expect that there'd be perturbations on term, but you can hide it with it. You know, let's say you want to like, you're an alien civilization, you want to like see for chill, and somehow you can see through the sun, but we can't. You're good, right? Okay, these are the runner forms. We'll talk about how we form them. Probably not until Tuesday. So we'll need to talk about all of the orbital dynamic basics. And we'll come back to this, but stuff can live here in a two-body system. So in fact, we see this in the solar system. We see asteroids that hang out here and here. Certainly see that in the context of these moons called Janus and Epimetheus, where it's fucking sick. They are both going around Saturn and they swap places like this around Saturn. One gets closer, one gets farther, one gets closer, one gets farther. So I'll show you how that can happen. It's one of the coolest things in the solar system. If you like, you know, are hardcore. Okay, there's an example. Don't look, get away with that. Okay. Okay, so let's say you have two moons. Let's say you have this inner satellite and an outer satellite. These resonances can trap particles, right? So you're always pulling that ring apart, so it can't coalesce into its own objects. It doesn't fall, like so it clears out the radius in its whole sphere. But then this material never has the ability to coalesce into its own little particle because it's constantly being disrupted by its two friends. Its two shepherding moons are pulling apart whatever. Okay. And so you have a lot of this structure. So you had like a lot of closely spaced nested orbits with little satellites in between, and you can see those ripple things. So here you have Prometheus on the inner side of the F ring. This is the F ring. There's Pandora. What this is essentially doing, both of these together are shepherding the F ring so that it doesn't diffuse. This is a very thin ring. It doesn't have a lot of material to start. And yet everything in here is already gone. We can talk about why there's a gap in here, but it's not even. So whatever's happening to these particles is not happening to this particle. It's the moving shiver. That is James. Remember we talked about Janus and Epimetheus? Janus, Epimetheus. Got it? Let's see that one more picture. Yeah, here we go. Bam. Good. So here you see some of the structure, and I hope you can see that these little ripples going through looks like that here. This the bright and the dark, the bright. Those are those gravity, not gravity. Those are those radial oscillations and vertical oscillations in the wave structure itself, all the way through. Okay. And you can see that there's a bunch. So even though this F-frame, if you zoomed in on it, and of course there's a radial structure. All right. Okay. So generally speaking, we can talk about the gravitational potential energy. and the moment of inertia of a uniform, spherical, uniform density object, right? So, uniform density spheres, we already said this one, 40%. That's where there's no differentiation. And, you can prove this. How do you prove that? What's the potential energy of a point? Mass M. The view of gravity is that's the next question. What's the force of gravity?
The big mass and the little mass.
Okay. Negative. First thing you have to say, okay, negative, really, really important, because this is an attractive force. Unlike electromagnetism, for Q, the charge can change, and it can be repulsive or attractive, it's only attractive. Good, so that's great, so we got this now, and this will be in the radial direction and everything else, and adding effective quantity, and we love it. What's the relationship between energy and force? Be very careful about how we use our words here. Adds force to it, what do you mean by that?
Well, I should say they all have a product.
Okay, okay. So you might have something like this, x, and then dx dt is v. And if you then multiply mv, that's your momentum. P. And if I do dp dt, that's F. Similarly up here, if I do dv dt, that's A. Good. So this is what we tend to use, but this is right. Right, and you see that in class a little bit more. Okay, so now there was a relationship. You said something about a distance. So U is what? Let's just say generally, when we're writing these types of terms, F and everything. How do I relate F's and U's? Force times F. Force times how far it is, we're almost there. The definition of energy is force applied over some distance. Right? And because we're mathematicians, we assume that the force is not always applied equally. So we'll do something like F D L. Right? And because this is a scalar quantity and these are vector quantities, how do I connect them?
Well, vector times the vector creates a scale.
Not always. What's that?
Oh, the dotted.
There we go. Okay, so the dot product produces a scalar. This produces
That produces another vector.
another vector. Very good. Which vector do you know? You do know. You all know. This is the torque. You see that torque and energy have the same units? One of them is a vector quantity, one of them is not. Okay. All right. Write all that down. This you need to be able to do by heart. You have to intuitively understand how they work. You start with position. You get to velocity. Velocity gives you acceleration. Normally from acceleration, you get force, and you're done with 2,500. But then you get a little bit wiser, and you realize mass can change. So you talk about momentum. You say I could lose mass, or I could change velocity. Both of those will contribute to forces. So I say the rate of change of the momentum is the force. Right? I'm like, okay, now I really got it going. And then I say, okay, I'm going to add up the forces over some distance. I'm going to say that I forced it here, forced it here, forced it here, forced it here, and that will be the change in energy. And similarly, if I think about a force, but it's not applied in the direction that I'm considering, that's a torque. Right? Let me give it I need a long thing. I never have long yardsticks. I'm not going to delete this. I'll keep this up for the rest of the work. Okay, here's my object. Right? What's it being? What are the forces on it? What? Good. Where? Which direction? Three down. Good. All right. Right. So it fell. Good. It fell over some distance. So I can calculate how much energy it needs. It's not rotating fast. What was different?
We had a rotation.
Yeah, but why? Let go of one side. So this side started to fall, right? But look, notice that the direction of the fall, the distance that it started moving, is not the distance of the force, right? So the weight is pulling it down this way, and yet it's moving in another direction. That's a torque. Simple? Okay. Memorize it inside your body. Feel it deep in the hole. Okay. This is all of mechanics. Nothing else exists. I mean, everything else exists, but it's just harder versions of that. Okay. Okay, so let's go back to the biggest question. How do I write U? So now I have something to write U. So what should this be? Yeah, something similar to that, but maybe for this. So for the gravitational potential of a point source, you might get something like G M, right? Little m over. Good, very good. And am I done? Negative, right? Because we remember that the gravitational potential is negative constant. Now, could I have shown that? Could I have taken this thing and done an integral? Yeah, I definitely could have done that. And you might want to do that at home. Because all you have to do is just take this and turn this into dr and integrate from 0 to some distance. Right? Little r. Boom, you're going to get this answer. Okay. But how the fuck did I get that? Oh, Chris Money, you're such a liar. Okay. Yeah, so now this is for a point source. So let me change what I'm thinking about. We're gonna do this together. Now I have some, there's some body M. But it's M of the whole thing. So now I need to have some radius R and some density. Right? How do I define density again?
That's it.
Mass, total mass over total volume. Okay, and we might have to write like differential qualities, right? Okay. So I'm gonna show you how to derive that. We're gonna do the derivation of U. But this is how we measure the interior of bodies. We fly over them, okay? And we measure whether or not they're differentiated by looking at their gravities. These things are gonna be related, I promise. Okay. All right, so here it comes. Oh! All right, I promised you du. Look at that. SPL. You fucking take that shit. All right, we can integrate that. Right, the DL, I told you it's gonna be R squared, or sorry, DR. Right? But R squared's on the bottom, that's perfectly fine. The only thing is here, we have to be a little careful. So I'm taking every little piece of material DM. And every little distance. And I have to take M and put it in terms of things that we like. So I would say the density times the volume. But I need to represent that in terms of the total. So I would say little m, how much material is interior to some sphere, right? So let's say I start here, this is my little r, and it encloses some little m. As opposed to the whole sphere, which encloses big R, and it is the total. And then, of course, because it's spherical symmetry, those things are just cubed in the ratio there. So I can say very easily how much material is 1/3 of the way out. 1/3 cubed is 1/27. There's not a lot of material in the uniform sphere at the very center. Almost all of it is farther out, the object's bigger. So the gravity won't be very big. That's all I'm thinking about there. So now we take M, and I gotta differentiate it. There's DM, little piece of M that we need in order to do this integral. DM. So it's the density, which I can use here by rearranging. Right? Times R, wherever I am. And all my spherical coordinates. Now these ones are not going to hurt us. Okay, sine theta, d theta, d phi. You're going to integrate that. It's uniform. What are you going to get? And the other one? Oh. Yeah. I'm 2 pi. 2 times. This one you can know. This you see a lot when it's spherical symmetric. Just throw that in. Oh, okay, I have to remember that this piece here, right? That piece there that I'm not covering up, that's for one. Cool. Okay. So we do some rearrangey-bangey, okay, bada bing, bada boom, DM goes in here. DR is the thing that we're integrating over. I'm very scary looking. Horrifying, perhaps. But most of the terms can be done independently. So here is your, right, 2 pi. Here's your 2. Those multiply each other. 4 pi. Good. Okay, so that's easy. This piece here, r prime to the 5th. I know how to integrate r prime to the 5th. Right? That's straightforward. It's minus r to the 5th over 5. And similarly, this one is r to the minus 2. Know how to integrate that as well over r prime. Good. All right. That takes us to the end of it. I would deeply, deeply recommend you try this on your own. Touch up on these skills. And that's the value you get, minus 3/5. Really ran out of time here. Okay, we'll be trying to describe this really briefly, and then we'll just go directly into the idea of orbits in the first place and go into like the Lagrange stuff we were talking about. So the idea is you can measure a lumpy thing by imagining it circular and then using Legendre polynomials, which are just loops that you can add in successive approximations to say, well, it's kind of got a loop here, right? It's got a loop here, so I'm going to add this, but I'm going to subtract this. So these pieces get rid of, and this piece gets rid of this, and it only adds. So you can build up. This is what mathematicians do, they're super cool. And they can just build up an approximation of the object using these Legendre polynomials, right? The same way that you can, if you've ever seen like a Fourier decomposition, you start with a sine wave, beautiful. You add 2 sine waves, you're like, ew, that's a little gross, has these lumps in it. If you add like 15, you can build a square. You can build a square wave with like 15 sine waves. Fuck, that's not what it's supposed to do. So you can take any periodic function and you can decompose it. Similarly, you can take any shape and you can break it down into Legendre polynomials. And we'll use this, and we'll measure deviations from circularity to tell us about the gravity field. Tell us about where the mass is. Okay, thanks for your patience, folks. Any questions, comments, concerns?